I am Sheikh Rashidur Rahman, Assistant Professor, Department of Electrical and Electronic Engineering, University of Asia Pacific. So today I am going to deliver my third part of the lecture of fault analysis actually. So this is the slide which I have already discussed for symmetrical three-phase fault for some portion of the slide. Now today I am going to discuss about unsymmetrical faults. So if in three-phase transmission line, the types of occurring faults for three-phase are different, that is called unsymmetrical fault. For an example, if a single line is being short-circuited through the ground or into the ground, that is called single-phase short-circuit fault or line-to-ground fault. If two lines being shorted with each other, that is called line-to-line fault. And if two lines shorted with each other into the ground, that is called double line to ground fault. So for this type of faults, the current flowing through three transmission line or three different line have different parameters. So that's why that is called unsymmetrical faults. It means that the system is no longer being balanced whenever this type of fault occur in transmission line. So sequence network means actually we have already known that three types of symmetrical component we have, like positive sequence symmetrical component, negative sequence symmetrical component, and for zero sequence symmetrical component. So for these three types of symmetrical component, or for these three types of uh, symmetrical voltage or current, there should be three different sequence network. Like for a transmission line, we can draw a circuit, and from this circuit we can calculate the voltage, current, etc. So now where I'm going to discuss about the sequence network of load. At first for Y connected load, then delta, then the generator, motor, transmission line, and transformer. So now this is a sequence circuit of a three-phase Y connected load. So if this is a three-phase load and this is a Y connected load, then the circuit diagram or the figure connection diagram of the load look like this. Here, neutral is grounded through an impedance that is Zn. So through an impedance that is Zn, and here every phase has a impedance that is denoted by Zy, and the phase currents are respectively IA, IB, and IC for phase A, B, and C. Here the line-to-line voltage differences, that is VAB, VBC, and VCA, and the line-to-neutral voltage difference, that is VAN, that is A phase to neutral, and the neutral to ground voltage difference, that is VN, the voltage difference between the neutral to ground. So now if we want to calculate the neutral current IN, that should be the summation of the total current. So IN or neutral current is equal to IA plus IB plus IC. That's the summation of total current. Now VAG, that is the A phase to ground voltage drop or difference, VAG. That means A phase to ground voltage difference, A phase to ground, that is two voltage drop should be sum of one from A phase to the neutral, that is VAN, and another one from neutral to ground, that is VN. So A phase to neutral, so the voltage difference is VAN. So the equation should be voltage V is equal to I into impedance IZ. So VAN should be VIA, that is the current, into impedance of phase A, that is ZY. So VAG is equal to at first VAN plus VN. So AN is equal to AY into ZY plus VN should be the voltage drop between neutral to ground. So that should be IN into ZN. So IN into ZN. Now we can put the value of neutral current, that is IN is equal to I plus IB plus IC. So if we put the value of IN here, the equation should look like this. Similarly, we can write down for the voltage of VBG, that is the B phase to ground, and similarly for VCG, that is C phase to ground. Now, these are the three equations, and we can write this equation in a matrix form to solve the equation more easily. So if we write down these three equations in a matrix form, then left side of the matrix or very left matrix, that is denoted the line to ground voltage VAG, VBG, and VCG, and the very right side of the matrix, that is denoted the three phase current, that is I, IB, and IC, and the middle matrix is the impedance matrix or the coefficient matrix in the equation of phase to ground voltage. This is the impedance matrix. So now we can, if we want to convert the phase voltage and phase current to the symmetrical component, then we can write that the phase voltage should be impedance matrix into current. Now the phase voltage is equal to A matrix into symmetrical component of voltage, because we want to develop the sequence network, that is the positive, negative, and zero sequence network of the system. So for this reason, we have to identify the symmetrical component of current and voltage, and we have to introduce the symmetrical component of current and voltage in this equation. So that's why we just convert the phase voltage to the symmetrical component of voltage, and the equation is phase voltage is equal to A matrix into symmetrical component of voltage. Similarly, the phase current is equal to A matrix into symmetrical component of current. So now, if we want to find out the equation of symmetrical component of voltage, then A should be just move to the right side of the equation. So then should be A inverse. So the final equation should be, after calculating the zero sequence voltage, the positive sequence voltage, and the negative sequence voltage matrix is equal to the impedance matrix into sequence component of current. So now, from this equation, we can easily separate the three different sequence voltage equation. That is the zero sequence voltage equation V naught is equal to I naught into ZY plus 3ZN. Positive sequence voltage equation V plus or V1 is equal to I plus or I1 into ZY. Similarly, the negative sequence voltage equation V minus or V2 is equal to ZY into I minus or I2. So from these equations, we can write, or we can draw the sequence network. So the positive sequence network of a Y connected load, the positive sequence network, the equation, the diagram should look like this. So here, the positive sequence terminal voltage, that is the VA plus or V plus, this is the positive sequence terminal voltage, that is equal to the positive sequence current into positive sequence impedance. So I plus or I plus is the positive sequence current, and ZY is the positive sequence voltage here. So this is the positive sequence network, because there are single drop, there is a single drop for positive sequence voltage. Now for negative sequence diagram, the negative sequence voltage V2 or V minus is equal to ZY into I minus or I2. It means that the negative sequence terminal voltage V minus is equal to negative sequence current into the negative sequence impedance. Now for zero sequence diagram, the V naught or zero sequence voltage drop is equal to the zero sequence current into zero sequence impedance. So the zero sequence current, that is the I0 or I naught into the zero sequence impedance. Now for zero sequence impedance, there should be two impedance is just sum here. One is the sequence impedance, that is for zero sequence impedance, and another one is the neutral impedance, and we have to add this neutral impedance by multiplying 3 with the sequence impedance if the neutral is connected through an impedance. So the diagram should be the zero sequence terminal voltage is equal to I naught, or zero sequence current. It should be multiplied by zero sequence impedance ZY into 3Zn. So these 3Zn is connected with ZY in series, because the neutral impedance should multiply by 3 and it should be add with the sequence network. So this ZY plus 3Zn is equal to Z naught. This is the zero sequence impedance. So it it should be happen if the neutral of the Y connected load is grounded through an impedance. Then this 3Zn. And how this 3Zn comes, we just develop the equation to prove that how this 3Zn comes there. So these are the sequence network. Now, if the neutral is open, it means that the load is in Y connected load, but the neutral is not grounded. So if the neutral is not grounded, it means that the impedance of the neutral, that is Zn, should be infinity. So there will be no current flowing through the neutral to the ground. So this should be infinity impedance Zn. So if Zn is infinity, then there will be no effect in positive and negative sequence circuit. Because negative and positive sequence circuit, there is no impedance is present here as present the neutral impedance. So there will be no effect in positive and negative sequence diagram. But zero sequence diagram has a effect, because here the neutral impedance is infinity, and we know that the neutral current In is equal to 3 into I naught. It means that the 3 times of zero sequence current is equal to the neutral current. So if neutral is not grounded, it means that neutral current is 0. So zero sequence current should be 0. So for this reason, for zero sequence network, there should be an open circuit. So neutral to ground, there is open circuit, and Zn is equal to infinity. So there will be no zero sequence current will flow through this circuit if the neutral is not grounded. Now, if the neutral is solidly grounded here, then this point N to the reference line or ground line is solidly short circuited. So there should be a single impedance for zero sequence network, that is Zy, if the neutral is solidly grounded, that is Zn is equal to 0 then. And positive and negative sequence network as it is remain constant or remain same. So if the network is del connected, or if the load is a delta connected load, then the sequence network, or what is the sequence circuit, the circuit derivation, equation derivation, and the circuit diagram is given here. So that is a homework for you. And now for the sequence circuit of a generator. So if this is a generator, then we know the generator is generated the voltage as a positive sequence network. So only positive sequence circuit or positive sequence network generator is generated voltage. So that's why for positive sequence network, this is the electromotive force or generated EMF symbol, EM. For positive sequence network, only this electromotive force is placed here. And this is the positive sequence impedance, and this is the positive sequence terminal voltage. So if we add the positive sequence drop to the positive sequence terminal voltage, we will find out the internal generated voltage. Now, if for this we want to draw for negative sequence network, then for negative sequence network, there will be no symbol of source, because generator doesn't generate the voltage as a negative sequence network. So that's why for negative sequence network, there will be no symbol of source, only negative sequence impedance, negative sequence current, and negative sequence terminal voltage. And if this is a Y connected generator and neutral is grounded through an impedance Zn, then the zero sequence network diagram should be ZZ0. This is the zero sequence impedance plus 3Zn. That is the series connected of neutral impedance multiplying by 3. So this whole is represent the Z naught, that is ZZ0 plus 3Zn. And this is the zero sequence current, and this is the zero sequence terminal voltage. Here also there is no symbol of source, because the source is our electromotive source symbol is only present for positive sequence network. So for negative and zero sequence network, there will be no symbol of source or electromotive source. Now for the transmission line, actually we know that there will be no generating source in the transmission line. So that's why the positive sequence network of transmission line is just the positive sequence impedance, nothing else. For negative sequence network, just the negative sequence impedance, and for zero sequence network, this is the zero sequence impedance for transmission line. Now for transformer, actually we know that for transformer, this is a non-generating device. Transformer doesn't generate voltage, it just transmit voltage from one end to another, and maybe it supply the voltage as it is, or it can step up the voltage, or it can step down the voltage. So this is called the transformer, transform the voltage or transform something. So now transform the voltage or current. So now there should be 4 different types of connection for transformer. It means that there are 2 separate portions. One is primary, other one is secondary. So primary may be delta connected and secondary may be delta connected, or primary and secondary both are Y connected, or primary is delta, secondary can be Y, or primary is Y, secondary can be delta. So there are 4 possible connection types for transformer. Now these Y may be grounded or maybe not grounded. So there is another possible connection. So that's why this is the 5 possible connection for transformer. That is the both side are Y. Here both side are Y at first group. This is the symbolic connection, and this is the middle column. This is the connection diagram, and this is the symbol diagram, and the right side column, this is the zero sequence network diagram. Now for first diagram or first row, this is both are Y connected, primary and secondary, but the primary portion is grounded and secondary portion is not grounded. So if both portion are not grounded, then the zero sequence current will not flow from primary to secondary. So that's why for primary portion where neutral is grounded, here represent the zero sequence impedance Z0, but primary and secondary is open circuit because there will be no zero sequence current passes through primary to secondary because the secondary is not grounded. And this is the N or neutral or reference bus. This is R. Now for second row, the symbolic diagram is both are Y, but both are grounded now. So if both are grounded, then from primary to secondary, there will be a zero sequence current. So there will be a zero sequence current flowing from primary to secondary, that is Z0, and through connected primary to secondary. For the third row, the connection type is now primary is Y grounded, but secondary is delta. So whenever primary is Y grounded and secondary is delta, that time there will be no zero sequence current flowing from primary to secondary. So there should be open circuit from primary to secondary. But whenever the Y is the primary portion, so there should be a zero sequence impedance. And here Y is grounded and secondary is delta. To represent this, here the impedance is grounded. Here the impedance is grounded to represent that secondary is delta, because we know in delta circuit there will be a circulating current. Now for fourth row, there is primary is Y, secondary is delta. It means that just similarly, primary and secondary is open circuit. So there will be no zero sequence current flowing from primary to secondary, and the impedance should be placed where the connection is Y. And final, rho is represent both primary and secondary at delta. So it means that uh, in both primary and secondary circuit, there should be a circulating current which just flowing between the loop of delta circuit. So the impedance Z0 is now connected both portion to the ground. It represents the circulating current, and primary and secondary is again open circuit. So we can draw the sequence network. So if we have to draw a zero sequence network for this power system online diagram, then we can easily draw the zero sequence network. Here, the generator is Y connected and grounded through an impedance Zn. So the zero sequence network for this generator should be ZZ0 plus 3Zn. So ZZ0 and 3Zn connected in series from reference to P point. So here 3Zn and ZZ0 connected in series from P point to reference or ground line. Now from P point, there are two parallel branch. One is R and another one is Q. So from R to T, in this point between R to T, there is a transformer, and there is a transformer, and the transformer primary is delta and secondary is Y. So if primary is delta and secondary is Y, then there should be an open circuit, and in which portion is Y, there will be an impedance. And here Y is not grounded, so impedance is not connected through the reference bus. So here this is the R and T, there should be an open circuit, and the impedance is shown in the Y portion, that is the secondary portion. Now from T to M, there is high voltage transmission line, so there should be an impedance that represent the transmission line impedance. So from T to M, there should be an impedance and it represent the transmission line impedance. Now for second parallel branch, that is between Q to S, there will be another transformer. So this transformer primary portion is delta and secondary portion is Y, and that is grounded. So primary to secondary is open circuit, and secondary portion there should be an impedance with connected to ground, because here Y is connected to ground. So Q to S, there should be an open circuit, and the impedance is placed in the secondary portion, and that is connected to the reference bus or ground, because here Y is grounded. Now S to M, there is another high voltage transmission line. So there should be an impedance represent the high voltage transmission line impedance. So S to M, there should be an impedance represent the high voltage transmission line impedance. Now from V, now from M to N point, there is another transformer, and this transformer primary is Y grounded and secondary is delta. So here in primary portion, there should be an impedance connected to ground. So in primary portion, there should be an impedance connected to ground. Now secondary is delta, so primary to secondary is open circuit. So M to N, this is the open circuit. Now in N point, there is another, maybe this is a motor. So this is the Y connected. So Y is not grounded. So there should be single impedance, that is the zero sequence impedance, and it is not connected to ground because Y is not connected to ground. So in point, there is only one impedance, that is the zero sequence impedance, and it is not connected to ground. So this is the zero sequence network. So this is another diagram. We can easily draw the zero sequence network for this diagram also. So this is your homework. So this is an example of sequence network. That is, we have to draw the positive, negative, and zero sequence network for this one line diagram of a power system. So this is the math. But before draw the sequence network, we have to convert the all impedances of the device, including the transmission line, to a new base per unit value. So you have to change the reactances to new base, so new per unit value, uh, based on the new given rating in the question. So for this math or this kind of math, we have solved this per unit math for positive sequence network or for negative sequence before midterm exam. So in this point of view, or regarding this context, I just only discuss about the zero sequence network. So here, draw the negative, positive, and zero sequence network for the system. Assume zero sequence reactances for the generator and motor of 0.05 per unit. So for generator and motor, zero sequence reactance are given here. That is the 0.05 pu. A current limiting reactor of zero point 0.4 ohm is in each of the neutral of the generators. So here there are two neutral connected to an impedance for generator and another one is for motor M1. So these two neutral impedance has a value of zero point 0.4 ohm. Now the zero sequence reactance of the transmission line is 1.5 ohm per kilometer. So zero sequence reactance of the transmission line is given, that is the 1.5 ohm per kilometer. So we have to convert these reactance in per unit at first to draw the zero sequence reactance diagram. So the transformer reactance for zero sequence are not given in the question. It means that the positive sequence reactances of transformer T1 and T2 are same for the zero sequence network. Now at first here our base is 20 kilovolt for the generator base and MVA is 300 MVA. So for generator, the zero sequence reactance is 0.05 and the base value of power and voltage are same for the generator. So we don't need to calculate the zero sequence reactance for new base for the generator because that should be 0.05 per unit. So we have to calculate the zero sequence reactances for the motor. And for the motor, the zero sequence reactances old is that is the given in the question 0.05 per unit, and the new power base is 300 MVA divided by old power base for motor M1 is 200 MVA and for motor M2 that is the 100 MVA, and the old voltage for motor M1 and M2 is 13.2 kilovolt and the new base voltage is 13.8 kilovolt. So we can easily calculate the zero sequence reactance for the motor M1 and M2, that is 13.2 kilovolt, that is the old base, 13.8 that is the new base, and this is the 300 that is the new power base, and 200 is the old power base for motor 1 and 100 for the old power base for motor 2. So we can easily calculate the per unit reactances for M1 and M2. Now here we have to calculate the 3Zn, that is the neutral impedance, three types of neutral impedance for generator and for motor M1. Now the current limiter reactor is 0.4 ohm. So we have to multiply its 3. So 3 into 0.4 ohm divided by the base value of the impedance. And we can easily calculate the base value. The equation should be kilovolt square divided by megavolt ampere. So kilovolt for generator portion, that is the generator circuit, the base voltage is 20 kilovolt. This is the new base voltage. So for generator circuit, the base impedance is kilovolt square divided by megavolt ampere, and kilovolt square is 20 kilovolt square. That is the 20 square divided by 300. So that is for generator side, 20 square divided by 300, 1.333 ohm. This is the base impedance at the generator circuit. Now for the motor circuit, the new base voltage is 13.8 kilovolt. That is the new base voltage. That is the 13.8 kilovolt. This is the new base voltage. So the new base impedance for the motor circuit is 13.8 square divided by 300. So 13.8 square divided by 300.625 ohm. So we can easily calculate the per unit impedance for the neutral impedance, per unit impedance or per unit value for the neutral impedance. We can easily calculate this. And for transmission line, the zero sequence impedance is 1.5 ohm per kilometer, and total length is 64 kilometer. So you have to multiply 1.5 into 64 divided by the base impedance, and base impedance is kilovolt square divided by megavolt ampere. Here the transmission line base is 230 kilovolt. So 230 square divided by 300, that is 176.3 ohm. So here we just calculate the per unit reactances for zero sequence network, and here we can draw the zero sequence network also. From our main power system online diagram, the Y is grounded through an impedance. So for zero sequence diagram here, at first a zero sequence impedance is connected with a series, that is the 3Zn or neutral impedance 3 times. This is at first for generator, and here for generator this is the 3Zn and with the zero sequence impedance. Now here there is a transformer T1, primary is delta, secondary is Y grounded. So there should be an open circuit from primary to secondary, and for secondary portion there will be a zero sequence impedance connected to the ground. Then this is the high voltage transmission line impedance. For transformer T2, at first primary portion is Y grounded. So primary portion there should be an impedance, and another portion is connected to the ground, and secondary this is the open circuit. After this there are two motor, one is just M2, that is only zero sequence impedance, and this is not connected to the ground because the ground is not connected to the neutral of the motor M2. But for motor M1 there will be as the connected, there will be a connection for neutral to ground because there is a connection between neutral to ground through an impedance. So that's why 3Zn series with the zero sequence impedance. So this is the diagram here. So this is the open circuit, then this is the reactance for transformer T1, this is the reactance of high voltage transmission line, and this is the reactance of transformer T2. And again this is the open circuit, and here two motor connected to the parallel. M1, this is a neutral impedance 3Zn with the zero sequence impedance of the motor, and for M2 there is only a zero sequence impedance. This is the not connected through the ground. And that's all for the unsymmetrical fault analysis slide here. So this is the third part of fault analysis lecture.